If you've ever stood on a platform and watched Japan's bullet trains pull in, you've probably noticed something odd. Their noses are wildly different lengths. The Hayabusa on the Tohoku Shinkansen has an absurdly long pointed nose. The Komachi on the Akita Shinkansen is also very long, but the Kagayaki on the Hokuriku Shinkansen is noticeably shorter and rounder. Probably just aerodynamics, right? Today, let's dig into why Japan's Shinkansen noses are actually different lengths and why aerodynamics alone doesn't even come close.
The biggest factor here isn't simple air resistance. It's what happens the instant a high-speed train hits a tunnel. When a Shinkansen enters a tunnel, the air in front of it can't get out of the way fast enough. A compression wave is born right at the tunnel entrance.
That compression wave then races through the tunnel at the speed of sound, and when it reaches the other end, it radiates outward as a pulse, a small but very real boom. In Japan, the engineering term for this is tunnel micro-pressure wave, sometimes informally called a tunnel boom. So the shape of the nose isn't styling, it's fluid dynamics.
Here's the subtle part. Reducing air resistance and smoothing the pressure rise look similar, but they're not the same problem. J.R. East's own technical papers say that as speed goes up, the micro-pressure wave gets dramatically worse, and that's why they keep refining the nose profile and cross-section.
So a long nose isn't really about slicing through the air, it's about not slamming the air all at once. Even with the same nose length and the same cross-section, the exact shape changes how steep the pressure rise becomes, and that's documented in their engineering reports.
So why is the E5 series, the Hayabusa, so extreme? According to J.R. East's official spec, the E5 is designed for 320 km per hour running, and the long nose is there specifically to suppress high-speed noise and tunnel micro-pressure waves generated at that speed. A technical review goes further. The E5 is based on an earlier prototype called Fastech 360, but the production nose was shortened from 16 meters to 15 meters to recover passenger seating capacity. So the E5 isn't just fast, it's a 320 km per hour train that also had to preserve interior space and meet environmental noise limits, all packed into a 15-meter nose. Next, the E6, the Komachi. Its official documentation says the E6 uses the same long nose philosophy as the E5 for stable 320 km per hour running in the Shinkansen section and to suppress tunnel pressure waves. The pre-production release adds that the E6 inherits the E5's nose concept while also handling the tight curves and narrower clearances of conventional Japanese rail lines. The E6's nose is around 13 meters. Why shorter than the E5? Because the E6 runs at 320 km per hour on the Shinkansen tracks, but it also has to fit through older, narrower conventional lines to reach the city of Akita. The design philosophy is E5-like, but the constraints aren't, and that's why it can't be a copy of the E5. Now the E7, the Kagayaki. This one needs a small caveat. J.R. East's current public listing gives the E7 a top speed of 275 km per hour. But the original development documents for the Hokuriku Shinkansen designed it around 260 km per hour.
The same documents note that the Hokuriku Shinkansen route is harsh, 3% gradients, a switch in electrical frequency midway along the line, and so on. For the nose, the engineers kept environmental performance, tunnel waves included, but wrapped it in a simpler, streamlined form they called the one-motion line.
That's where the E5, E6, and E7 split. On the E5 and E6, the headline words are 320 km per hour, high speed, tunnel micro-pressure wave, long nose. On the E7, the framing is different. Keep the environmental performance you need, then optimize for the Hokuriku route's specific constraints. A different shape for different conditions.
So the noses look inconsistent, but that's not sloppy design. It's the opposite. Different top speeds, different routes, different capacity targets. Optimize for all of those, and the E5 lands at 15 meters, the E6 at 13 meters with conventional line constraints, and the E7 settles on the compact one-motion line. The shapes aren't random, the conditions are.
If you try to explain all of this with just drag reduction, you lose most of the story. What really determines the nose length of a Japanese bullet train isn't looking fast. It's a total design optimization across speed, tunnel pressure waves, line-side noise, cabin space, and the specific route the train has to survive.
So the Hayabusa's nose is long because it was optimized hard for the Tohoku Shinkansen's conditions. And the Kagayaki looks short because it took a completely different optimal solution for the Hokuriku Shinkansen's conditions. Same engineering goal, radically different shapes.
Thanks so much for watching all the way to the end. On this channel, from an engineer's point of view, we dig into the everyday mechanisms around us, the ones you thought you knew, but maybe never quite understood. If today's story sparked even a little curiosity, I'll see you in the next video.